So we've talked about polar versus nonpolar bonds. The polar bond is one in which the electrons are shared unequally. You think of it as one person hugging the blankets when two people are sharing a bed. The blankets being shared but not equally. So if we have a simple molecule, just two atoms, a diatomic molecule, there's only one bond, and if that bond is polar, then the molecule is polar as well. We can depict it this way with an arrow pointing towards the more electronegative element with a plus sign at the other end. That indicates that this chlorine end of the molecule will have a slight negative charge. The hydrogen end will have a slight positive charge. We could also depict it like this, showing the electron density. There's more electron density here, less here. We can also indicate it with the lowercase Greek delta, D minus and D plus, indicating partial charges. So that's a diatomic molecule. In a polyatomic molecule, the polarity of the molecule is going to depend on the geometry. If the dipole moments of individual polar bonds cancel each other out, you can have a nonpolar molecule even though it has polar bonds. Let's look at an example. Carbon dioxide. So carbon dioxide has 3 atoms in it, the carbon's in the middle, 2 oxygens bonded to it. Each of these carbon is attached by a double bond. So if we look at Vesper theory, we look at the number of electron groups around the central atom, there are 2. Each double bond is one group, so there are 2 groups. 2 groups arrange themselves on opposite sides. So this has a linear geometry. These bonds are nonpolar. Carbon and oxygen, not the same element. Oxygen is closer to fluorine, therefore we predict it's more electronegative. So the oxygen is going to pull the electrons away from the carbon. That's going to result in the oxygen end of this bond being slightly negative and the carbon end being slightly positive. But on the other side of the molecule, the same thing is happening. And oxygen is pulling electron density towards this side as well. So the net result is that there is not a positive or negative end to this molecule. There's a decreased electron density in the center, but both ends are the same. So you can imagine this like 2 people playing tug-of-war. So we had 2 people here. I should really think these things out ahead of time. So there's the rope, and there's like, a red flag or something hanging on it. So this person is pulling that way, this person is pulling that way. If those people are equally strong, is the flag going to move? No, it won't. So there will be no net movement of the charge in that molecule. You won't have one end that's positive or one end that's negative. Does that make sense? If this person was much stronger, then that person would pull the electrons more than the other one would, and it would be a polar molecule. So when we talk about a dipole moment, we're talking about a single bond can have a dipole moment if it's a polar molecule. A polar bond, it has a dipole moment. But dipole moments are vector quantities, meaning they have a direction as well as a magnitude. So the direction is indicated by the more electronegative element in the bond. The magnitude is going to depend on the difference in electronegativity between the 2 atoms. So for this molecule, CO2, the vectors are pointing in opposite directions. So they're pulling against each other. And the magnitudes are equal, and so those vectors add to 0. If we look at water, water also has 3 atoms, contains 2 polar bonds, but the Lewis structure for water has lone pairs on the central atom. So when we look at that Lewis structure, we count 4 electron groups around the oxygen. How do 4 groups arrange themselves? Tetrahedron. So it's going to make a tetrahedral electron geometry, but then 2 of those things are lone pairs, so they're like invisible. And so what we have left is what's called a bent structure. It is not linear. So here we have the oxygen pulling electron density from the hydrogen and the oxygen pulling electron density from the other hydrogen. The hydrogens are not pulling in opposite directions or being pulled in opposite directions. And so what I imagine here is that, say this is Dad. Dad is strong, and here's 2 little boys, his sons, right? And they're trying to pull the rope away from Dad. And they're pulling at these angles. But overall, what's going to happen to this group of people? Dad's going to move this way, right? He's pulling against both of the little kids, and so he's going to be able to just back up, and the kids are going to come with him. In carbon dioxide, you've got the forces opposing each other. They're going in opposite directions, and so there's no movement if you think about tug-of-war. So water is a polar molecule. The oxygen end is slightly negative. The hydrogen end is slightly positive. Anybody have any questions? So how do we identify the shape of a molecule and its polarity? So first we start with the Lewis structure. We determine the molecular geometry. Then we're going to look and see, are there polar bonds? If there are no polar bonds, then it's simple. The molecule is nonpolar. Frequently, though, there are polar bonds. So then we indicate which bonds are polar, and we identify the direction that they're pointing, and the length of them, which is proportional to the difference in electronegativity. And then we decide, well, do those vectors add up to a net dipole or to 0? If they add to 0, the molecule is nonpolar. If it adds to something other than 0, the molecule is polar. This is the full description of how polarity of a molecule is determined. That's a little over the top for our purposes. So here's the short, well, I guess we have to talk about vector addition, but I'm going to give you the short version here first. So here's my shortcuts to molecular polarity. So a molecule is nonpolar if both of these things are true. No lone pairs on the central atom. Come on, arrow, there we go. No lone pairs on the central atom. And all the atoms that are bonded to that central atom are either the same type of element or they have the same electronegativity. If that's true, the molecule is nonpolar. If one of those is false, the molecule is polar. So let's go back and look at vector addition, because we're supposed to. You should have learned about this at some point in math class, but you probably deleted that to make room for more important things. So review of vector addition. So if we look at vectors in one dimension, these vectors lie on the same line, and we just assign a direction as positive. It could be, if we're looking at a horizontal line, it could be to the right, it could be to the left. It's a bit like a number line. So, here's 0, 1, 2, 3, etc., and -1, -2. We just decide this is how we're going to draw it. Then you put those two vectors on that line, pointing in the correct direction. So in example 1, we have vector A and vector B are pointing in the same direction, and they both have magnitudes of +5. So starting at 0, going +5 for the one, and another +5 for the next one, the sum of those two vectors is a vector with a length of 10. Does that make sense? In example 2, we have vectors pointing in opposite directions. So we could represent vector A as being a -5 if this is just a one-dimensional system. So this vector is -5, so going to the left 5, and this vector is +10, so 10 to the right. And then when you add those two things together, you could go starting at 0, you go over -5, and then you go +10, and so you're going to end up with a net vector of +5. Does that make sense? If you think about this as playing tug of war, with the ends of these vectors as the flag, and this person is pulling in that direction with a strength of 5, this person's pulling in the opposite direction with a strength of 10, this person wins, right? Here, both are pulling in the same direction. They're going to go even farther. Here in example 3, we have vectors of the same magnitude in opposite directions. And so they will cancel each other out. Those add up to 0. Any questions about that? We have to understand vector addition in one dimension before we can look at 2 or 3 dimensions. And all this is really is a number line adding positive and negative numbers. So what we do for 2 or more dimensions is you take your two vectors. Here I've got A going in this direction and B going in that direction. The length of the line represents the magnitude, and the direction obviously represents the direction. So you put their starting points together, and that forms two sides of a parallelogram. So a parallelogram has opposite sides that are parallel to each other, hence the name. So here's A, I can draw a line parallel to A. Here's B, and the dotted line parallel to B. And the sum of those two vectors is the diagonal of that parallelogram. Here's another example, this one going off here and this one going here. We complete the parallelogram, and the sum is corner to corner. Any questions? The good news is you can be pretty successful at predicting molecular polarity without understanding vector addition. If you're adding 3 or more vectors, you just look at them 2 at a time. So add 2 first, and then take the result of that and add the third. If you've got another one, take the result of that and add the fourth. Here we have, again, this is happening in 2 dimensions, but we're adding 3 vectors, A, B, and C. So we can add A to B, completing the parallelogram, and draw an angle, draw the diagonal, and then we're going to take that, that's the sum of A and B, we're going to add it to C, again by making the parallelogram, and the diagonal is the sum. Here in example 7, we have A, B, and C are the same magnitude, and they're going off in directions that are equally spaced. So if we add these two, A and B, we get this vector R. If we add R to C, those cancel out, and the vector is 0. So this is would be nonpolar because the vectors all add to 0. Is that disturbing?
For example, I'm just not sure. You gave
This first R is from adding B and A and B. So we can't add three things at once. We just take them two at a time. So we add A to B, and we get this R. Then we're going to take that red R, and we're going to add it to C, and we're going to get the purple R prime. Okay? Any other questions? So these are common cases of adding dipole moments, adding vectors in molecules. If you have a linear molecule, you'll often end up with a nonpolar molecule, provided that the magnitudes of those vectors are the same. If you have a bent molecule, you're going to end up with a polar molecule because those vectors at angles cannot cancel each other out. Here we have a trigonal planar molecule. If the vectors have equal magnitudes, they're going to cancel each other out. If we have a tetrahedron and the magnitudes are equal, those will cancel out. If we have a trigonal pyramid, they will not cancel out. Okay? So that's the thorough explanation. But this one works too. This doesn't work all the time, but it works, 90-95% of the time, which is pretty good, actually. So this is mostly what I'm going to be talking about when we predict molecular polarity. And being able to predict whether a molecule is polar or not is very important in organic chemistry. So let's look at this molecule, CF4. Determine if CF4 is polar. We have to start with a Lewis structure because lone pairs on the central atom make a huge difference in polarity, and you can't always tell just by looking at the formula. So first we need to draw the Lewis structure for this. So we'll put carbon in the middle and the fluorines around the outside. We'll count up the number of valence electrons. Carbon has 4. There are 4 fluorines and they each have 7. So that's what, 32 electrons? I already have some for the single bonds, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So there's my Lewis structure. I did that kind of fast because that covered that already. So my shortcut method says, look at the central atom. Are there any lone pairs? No. The next thing is, look at the atoms that are bonded to the central atom. Are they all the same element? Yes. So we have no lone pairs, and all the elements are the same. This is a nonpolar molecule. The shape of it will be tetrahedral. It's not flat. But those 4 polar bonds are spaced equally around the carbon, and their magnitudes are equal. So they will cancel out. They'll add up to 0. So this is nonpolar. So molecular shape and polarity are very important because it affects the chemical and physical properties of the molecules. So polar and nonpolar molecules have different properties. They generally do not mix. So you probably know from personal experience that oil and water do not mix together, right? You try that at home. Just use a bottle of non-creamy Italian salad dressing and shake it up, put it down. You can watch the oil come to the top and the water, which is the vinegar part, go to the bottom. The reason they do not mix is because the oil is nonpolar and the water is polar. So what we have in polar molecules, they act like little magnets. So here's a water molecule has a partially negative end and a partially positive end. This positive end of the hydrogen is attracted to the neighboring molecule's negative end. So like magnets, these are going to be attracted to each other. Can you pull them apart? Sure. That force of attraction is fairly weak, but there is a force of attraction there. In a nonpolar molecule, you do not have these dipoles, and so there's not that same attraction between the molecules. So it's a bit like this picture. We have some magnetic marbles and some regular glass marbles. And if you just jumble these up in a bucket or a bowl and mix them together, you can imagine what happens. The magnetic marbles clump up and stick to each other, and they exclude the glass marbles, right? The glass marbles get pushed out because they are not attracted to the magnetic marbles. Does that make sense? So this is like the oil molecules, this is like the water molecules. The water molecules are very much attracted to each other. And in order for them to get close, they push everything else out. It was kind of like a clique in high school. So now I can explain how soap works. I love it when chemistry explains everyday occurrences. You probably know from experience, if you get grease or oil, like Crisco or motor oil or something on your hands, you can't just rinse it off with water. If you get something sticky, like from a popsicle on your hands, some sugary thing, water just rinses it right off, no problem. But if it's greasy, you're going to need some soap, right? So water is polar. The greasy thing on your hand is nonpolar. They're not going to mix together. So this is how soap works. Soap has a polar head and then a long nonpolar tail. This nonpolar tail can mix in with the grease, the oil molecules. The polar head of the the polar head of the soap is attracted to water. And so what happens is you get something like this. So here's my glob of grease. And the soap molecules will put their tails into the grease because that's where the nonpolar tails feel comfortable, and the polar heads will be sticking out. And so you get this globule of grease with polar heads of soap molecules all around it. These polar heads are attracted to water. Water is attracted to those polar heads. And so now this glob of grease is basically disguised as a polar thing. And so it can move through the water. Any questions? So the soap is basically breaking the grease down into little tiny clumps, globules, sticking its tails in the grease so that their heads stick out and it looks like water, and so it can be washed away with the water.